Have you ever wondered what the smallest measurement of time could be? This question may seem puzzling at first, but it's a question that's intrigued scientists, philosophers, and thinkers for centuries. Time. It's a fundamental part of our universe, a dimension that we experience continuously. Just as we measure the physical world around us in inches, meters, or miles, we measure the progression of events in seconds, minutes, and years. But is there a limit to how small a slice of time we can measure or even conceive? Could time, like space, have a smallest possible unit? Time is a complex concept, and as we delve deeper, it becomes even more intriguing. It's not just a simple ticking of a clock or the turning of a day. Time dictates the rhythm of life, the unfolding of events, and the progression of the universe itself. But let's consider this. The world of the very small, the realm of atoms and subatomic particles, operates under a different set of rules than the macroscopic world we're familiar with. This is the quantum world, a realm where our intuitive understanding of time might not hold true. Could there be a fundamental, indivisible unit of time, a quantum of time, much like there is a quantum of action in the universe? This brings us to the concept of Planck time, named after Max Planck, the father of quantum theory. Planck time is theorized to be the smallest meaningful unit of time. But before we delve into the mysteries of Planck time, we need to understand the strange and fascinating world of quantum physics. So buckle up, because this is going to be a thrilling journey into the depths of the quantum realm. We're about to explore the fabric of reality itself, where time and space are woven into a tapestry of cosmic proportions. To delve into the smallest unit of time, we must embark on a journey into the world of quantum physics. Imagine a world where the laws of physics as we know them don't apply. In this world, reality is not what it seems. This is the world of quantum physics, a realm where particles can be in two places at once, where cause doesn't necessarily come before effect, and where time and space lose their conventional meaning. Let's take a step back and understand what quantum physics is all about. In simple terms, it's the study of the tiniest particles in the universe, things that are so small that the rules of classical physics just don't work anymore. Now, to help you visualize this concept, consider a digital photo. From a distance, the image appears continuous and seamless, right? But as you zoom in, you begin to see that the picture is made up of individual blocks of color, known as pixels. Each pixel is distinct, with its own unique color and intensity. Similarly, our perception of time might be akin to looking at this digital photo from afar. We perceive time as a continuous flow, second after second, minute after minute, and so on. But what if, like the digital photo, time is not as seamless as we think it is? What if, when we look really closely, time is actually made up of discrete, indivisible units, just like those pixels? This idea isn't as far-fetched as it might sound. In fact, it's a concept that stems from the heart of quantum physics. It suggests that time might be quantized or pixelated in a sense. Now, if time is indeed quantized, what would be the smallest possible unit? Just like a digital photo can't be broken down beyond a single pixel, there must be a smallest unit of time beyond which we can't break it down any further. In this quantum world, the smallest possible unit of time is known as Planck time. This concept, named after the physicist Max Planck, takes us to the edge of our understanding of the universe, and it's where we'll direct our focus next. A Planck time, named after physicist Max Planck, is incredibly small. It's so minuscule that it's nearly impossible to imagine. But let's give it a shot, shall we? To understand Planck time, let's first consider the speed of light. It's the fastest thing in the universe, racing along at nearly 300,000 kilometers per second. Now let's bring in the concept of a blink. In the time it takes you to blink your eye, light can travel almost 40 million kilometers. That's equivalent to circling the Earth 1,000 times. Impressive, right? But now, let's dive into the world of the unimaginably small, the world of Planck time. This is the time it would take for light to travel a single Planck length. And what's a Planck length? Well, if an atom were enlarged to the size of the observable universe, a Planck length would be about the size of an actual physical tree. So, we're talking seriously small here. Now, back to Planck time. In a single unit of Planck time, light travels just this tiny fraction of a millimeter. It's a period of time so brief that it's almost beyond human comprehension. But let's try to put it into perspective. If the age of the universe, around 14 billion years, were compressed into one single year, a single unit of Planck time would be less than a second. In fact, it would be a fraction of a nanosecond. Planck time is so infinitesimal that it's hard to wrap our heads around it. We're talking about a span of time so small, so incredibly brief, that even the blink of an eye is an eternity in comparison. Yet, as mind-boggling as it is, Planck time is a fundamental part of our understanding of the universe. It helps us bridge the gap between the world of the very large and the world of the very small, between the cosmos and the quantum. It's a concept that challenges our perception of reality and pushes the boundaries of our understanding. Planck time is so small that it's almost impossible to comprehend, but it's a fundamental part of our understanding of the universe. Why bother with something as tiny and seemingly insignificant as Planck time, you may ask? Well, the answer lies in the realm of quantum gravity and the early universe. Just as a tiny cog in a clock can be crucial for its functioning, Planck time, despite its minuscule size, holds immense significance in the grand scheme of things. Planck time is the key to unlocking the mysteries of quantum gravity. Quantum gravity is a field of study that seeks to describe gravity according to the principles of quantum mechanics, and it plays a crucial role in our understanding of the early universe. Quantum gravity theories often involve scenarios where space and time are not continuous, but are quantized at the Planck scale. Here, Planck time serves as the smallest possible increment of time, beyond which the concept of time may lose its usual meaning. Think of it like a puzzle. When you're trying to assemble a puzzle, every piece, no matter how small, is essential to complete the picture. Similarly, in the grand puzzle of the universe, Planck time is one of those crucial pieces. It's a fundamental part of our understanding of the cosmos and its origins. Without it, our picture of the universe would be incomplete, and our understanding of its fundamental laws would be limited. The early universe in particular is a period in the universe's history where Planck time becomes crucial. In the moments after the Big Bang, the universe was so hot and dense that the usual laws of physics as we know them break down. Under these extreme conditions, quantum effects of gravity become important, and Planck time serves as the natural timescale to describe these phenomena. So, while Planck time is unimaginably small, its implications are anything but. It's a fundamental concept that helps us peer into the very heart of the universe, understand its beginnings, and unravel the complex laws that govern its existence. Planck time might be tiny, but it has a big role to play in our understanding of the universe. So, we've traveled into the quantum world and back, all in the space of a few minutes. We've delved deep into the concept of time, unraveled its mysteries, and ventured into the realm of quantum physics. We've explored the significance of Planck time, a concept that might seem abstract, but is fundamental to our understanding of the universe. Let's take a moment to reflect on our journey. Planck time, named after the famed physicist Max Planck, is the smallest measurable unit of time. It's so unimaginably tiny that it's beyond our everyday comprehension. To give you an idea, a single second is made up of more Planck times than there are seconds in the entire age of the universe. That's truly mind-boggling, but why does Planck time matter? Well, it's a cornerstone of quantum physics, the branch of science that deals with the tiniest particles in the universe. Planck time helps us understand the quantum world, where the rules of classical physics don't always apply. It's a bridge between the familiar world we live in and the strange, fascinating world of quantum mechanics. And Planck time isn't just a theoretical concept. It has practical implications too. It plays a crucial role in technologies like quantum computing, which could revolutionize our world in ways we can't even imagine yet. It's also key to our understanding of the Big Bang and the early universe, helping us answer some of the biggest questions in cosmology. So while Planck time might seem like a distant, abstract concept, it's actually deeply intertwined with our everyday lives. It's a reminder of the incredible complexity and beauty of our universe, from the tiniest particles to the vast expanses of space and time. Next time you check your watch, remember, every second is made up of an unimaginably large number of Planck times.